thank you so much, and thank you so much for inviting me. It's I'm sitting in Stockholm. It's late here, so but it's nice to end the day with a nice discussion and presentation. And as we said before, I really encourage to sort of have conversations and questions during the presentation. I think that would be nice. So I've designed the slides a bit informally. So the title of this talk is called Price Discovery in Constant Product Markets, and that's originally a paper or a project from my PhD. So I graduated a year ago, but then this project has converged with another project that I'm working on together with Eric, Xingling, and Chang. So we have sort of merged these projects. However, I will try to present the ideas that I've thought about in my PhD, and then some small new things, and then I'm also interested in digging into and talking a bit about the data as well. So it's the talk is designed into sort of a short, very short introduction, and then I have just a theory part, which is very simple theory, but it's about the deterministic price impacts in the constant product market. And I know that you guys know a lot about this, so it would be very interesting to hear what you think, because I've tried to think about it a bit more economically, and sort of see, okay, so what are the impacts in this market. And then I have some empirical results for sort of classical price discovery. So if you're also interested in sort of the microstructure empirical part of this, you can ask me questions about that. And then I would like to end with talking a bit, if I have time, about the DEX data. So I'm maintaining a Python package that I've developed to parse data from Uniswap, both version 2 and version 3, together with also metadata from the decentralized exchange. And I'm planning to release this Python package, but it's still like a private repo. But if anyone of you wants data, or you have any, or you know any project that wants data, I can happily provide that. All right. So, okay, so sort of some motivation and introduction to this presentation would be that, so my co-authors and I, we ran a VECM model. So that's a vector error correction model, where we looked at data from Uniswap v3 and Binance. So this model would sort of show you where price discovery is happening. So which market is following which. And price discovery is basically happening only on Binance when you compare these two exchanges. And I think this is, so I've gotten comments on this previously when presenting, and I think it's sort of quite well known in the literature that price discovery is happening on decentralized exchanges. And I don't have a clear answer for exactly why, but it's my guess would be cost of trading and also frequency of trading, probably. But this, to me at least, I have several questions after running this VECM. So, for example, is there any price discovery on Uniswap? That's the first question, and I think also that if we sort of define price discovery here, you can think of it in a microstructure literature terms, where it's basically just a permanent price impact. So so when you read price discovery in certain papers, it's just talk about the persistence on price. But if you think of it more in economic terms, it will be sort of where prices are actually discovered.
Sorry, just to clarify, when we think
Yeah.
about price discovery is happening on Binance, that is suggesting we're comparing the of availability on both V3 on both Uniswap and Binance, right? So if there's not any like long tail tokens that doesn't exist on Binance,
Correct,
um,
correct.
which would not be the case, right?
Yeah, no, for sure, for sure. So this is so this regression is on USDC and Ether. So of
Mhm.
course, if you have any currency pairs that are not present on Binance, that then the picture will be completely different. That's correct. And I actually have some thoughts about that later as well. But then sort of another question is, okay, so what is actually happening on Uniswap, especially in these large currency pairs? And then also a bit related to your question there. So like the constant product market, and could that function without a limit order book, or when blockchains are getting faster and faster, will we converge to sort of limit order books in the blockchain space as well? Um, to me, it's not really clear. You had like this Gloston paper in the 90s. Are limit order books inevitable or something like that? Was the name of the paper? And I think there's still a lot to do to understand are DEXs inevitable, and sort of what are the competitive advantages.
The
Um,
that's the inevitability of LB. I think that's the one,
oh yeah,
the
yeah,
title.
yeah,
Yeah.
exactly. Yeah, yeah. Um, so exactly. So and then sort of I'm trying to think about sort of, is the constant product rule reasonable, which you probably have some thoughts as well about.
I have a question.
Yeah,
In traditional markets, if you have two order books that allow you to trade the same assets, there is like, what is the intuition? Which market more likely to be the one that's going to dominate the price discovery process? Like if you have two markets, two stock markets, one is big, one is small, so the big will has more power. So the
right.
question, if it's also related to liquidity,
Yeah,
or
I would guess so. Yeah, I'm not an expert on that, but I would probably think like liquidity, cost of trading, and size and frequency.
okay, yeah, interesting, yeah. I'm just curious if there is hidden explanation, not just because one is centralized and one is decentralized, that make Binance.
Yeah, I mean, uh, I don't know, so I can't I can only speculate, but this is so these regressions are run on mainnet first of all, so you have the 12-second block time. That could be one reason. I don't know what the trading costs actually are on Binance compared to Uniswap as well. I would presume it's cheaper on Binance. But then when you look at the liquidity graphs, you see that at least during certain points in time, Uniswap has really really high liquidity compared to decentralized exchanges. So yeah, but I don't have a clear answer. So the theoretical part here, like as I said, it's very simple, but I just want to establish on common ground so we can talk about the price impacts. And some sort of theoretical question to have in mind here would be, as prices update deterministically on the constant product market, how does trading impact price? So if we just for completeness start to sort of define an exchange pair, we can consider two assets here. So we can think of S as USD and Y as Ether, and then they have an exchange pair. And an exchange pair on this decentralized exchange, for example, Uniswap, is initialized by a liquidity provider depositing a positive amount of some dollar and some positive amount of ether into the liquidity pool associated with this exchange pair. So we have some dollars now in the liquidity pool and we have some ether. And at this point in time, we can define the mid price, or what would be equivalent to the mid price in a sort of regular market. So the marginal price, so the price of trading an infinitesimal amount of ether, for example. So this is the ratio of the dollar liquidity part of the pool divided by the ether liquidity part of the pool. And then the execution price. So this is the marginal price, but then the execution price, on the other hand, would be sort of the average price on a lob, where you sort of have to walk the book to fill your order. And the execution price for exchanging delta XT, so some USD for some ether, would be defined as the ratio between these two deltas, which we could also sort of rewrite as a typical sort of economics equation with price times quantity here. And the difference between the marginal price and the execution price we could call the price slippage here. And the execution price is determined by the constant product rule, as we know. So I will also, for sort of completeness, go through this so we all are on the same page with the equations. So in the constant product market, the execution price is determined such that the product of the inventory in the liquidity pool is constant before and after the trade. So we have the dollar part of the pool times the ether part, and it should be the same after the trade at T+1. Which means that we can write this out, that we add some part to the liquidity pool and then we withdraw some ether from the liquidity pool. And then, of course, we can solve for the quantities here. So we can solve for, let's say that we put in $10. We can solve for how much ether we get out of the pool. And now we can start to do some substitution with the equations here. So we can solve for the delta XT here in equation 5. So in the constant product equation. And we can substitute in this into the execution price. So we can get a more refined formula here for the execution price. And we can also look at some properties of the execution price. So we can see that the execution price is increasing as the trade size increases with a positive derivative. We have a positive second derivative, so this increase occurs at an increasing rate. And then we have some asymptotics as well. So for example, as a trader's desired quantity approaches the inventory of the liquidity pool, the execution price approaches infinity, which is also very nice. And then when either the pool gets sufficiently large or the order gets sufficiently small, the price slippage goes to zero. So we have a convergence of the execution price to the marginal price. But okay, so I think these equations are sort of the standard equations that we see. But I'm interested in rewriting these equations a bit differently. To sort of think about the economic meaning of these equations. So we can define two relative trade variables at this point. So we call this phi t xx, which is the dollar part of the trade. So how much dollar we put into the liquidity pool, for example, divided by the total amount of dollars in the liquidity pool, and then we define this variable phi t xy, which is the dollar part divided by the ether part in the liquidity pool. And then we can do a decomposition
Sorry,
of the execution price. Yeah. Yeah,
Quick
for sure.
question. What's the dollar? How do we get the dollar term here?
Which dollar part?
Because you're saying delta XT and delta and XT and YT are all in dollar terms, right? Not in the token themselves. And this dollar, it must be converted by from the token to the dollar term.
Oh yeah. Sorry. So this is just how. So like in this example, I'm just considering sort of X to be dollar and Y to be ether here. So we could think of it as I could just say X and Y, but or was that not your question?
Yeah, sorry. I guess my asking, so here when you considering these two phi terms, the first delta XT over delta over XT, and
Yeah.
it's straightforward because any price, take it as US dollar or whatever tokens, it's going to cancel
Yeah.
out. But the second term, delta XT over YT, the unit here, you have to convert Y to dollar terms, right?
Right. Okay. So yeah. Okay. Now I understand what you mean. Yes. So this first. Yeah. Actually, it was a long time I thought about that, but you're completely right. So this is unitless, right? It's but this one is a bit more weird because you have sort of you would need to convert it exactly. Yes, I understand. Let's keep that in mind and see if there's anything we need to think about, because I'm very much interested in what you have to say about that. So if we consider this term, we could do a sort of decomposition of the execution price. So we can just very simply rewrite the execution price to be equal to the marginal price plus this relative trade term here. And we have exactly the same properties, of course, the asymptotics and so on. But to me, this looks a bit more sort of maybe like a role model or something like that, where you have a trade price that equals the efficient price plus some trade cost. And we can simply solve for this trade cost to be the price slippage here as well. So to me, I think this is yeah, it's a nice way to sort of to write the execution price here.
So you think like sometimes people define the variable that you mentioned, that is the relative trade, as pool size, and basically the idea is that when you have enough liquidity and the trade side is relatively low compared to the liquidity, so your execution price will be pretty much the marginal price, right?
Right. Exactly. Exactly. So and that's sort of these sort of classical graphs with the spread. I sort of see it similarly here.
Yeah. Okay.
So yeah. So large relative trades, you get a higher execution price here. But then we can think about the marginal price again and sort of the price impact. And I think the price impact is what people in microstructure are very interested in. And also I think people in industry, especially sort of high frequency trading firms and so on, you want to look at what's your price impact for an order. So we can define here the immediate price impact of a trade. And in this market, it's also representative of all new information, both sort of public and private information. So I think that's worth highlighting in sort of, let's say, like an Hasbrook 91 model or some classical microstructure model. We usually think about the market makers providing when they do their quote revisions, they provide public information to the market, and only private information is incorporated into the price through trading. But since the liquidity providers in this market don't really update any quotes, and they only put in liquidity at the marginal price, so they don't really affect affect the marginal price in this market. So theoretically, I think we need to think of it as sort of all information is incorporated through the trades here. And so we can define the immediate price impact from sort of one transaction to the next in trade time, just by this very simple relationship here, right? So we have the mid price divided by the mid price at time t minus 1, and we can write this out like this, where the deltas represent the trade. And this is also sort of what we at least what I've seen previously in the literature. But we can rewrite this with this relative trade variable where we have the delta xt divided by xt. So by solving for the change in the liquidity pool in the constant product rule, and then using this relative trade variable, we can decompose or rewrite the immediate price impact into this 2 times this, as you pointed out, this unitless relative trade variable times the square of this relative trade variable. And yeah, what do you make of this? I mean, so you have it's extremely, it's extremely deterministic, of course, and we have this quadratic component in the price impact, which it's I'm having a hard time to really wrap my head around what it means. If it's, I mean, of course it just means that like you get the quadratic part will be more dramatic if the trade size is high or the liquidity is low. But what does it mean for the constant product rule in terms of its usability and so forth? I'm not really sure. We can plot this and just think about it a bit more as well. So the solid line here would be the price impact, and I also plotted the squared part here so we can see sort of how it increases when the relative when phi here, this relative trade increases. And I plotted something that I just called a linear range, which basically means that the square term is relatively close to 0. So we have a linear price impact, just 2 times phi. But then the empirical range is where the data is actually, so we have some really large price impacts in the data as well. And here we can see sort of that this squared term is getting more and more significant. And this is for USDC Ether. And so this is a very liquid currency pair. And I'm thinking also how this would look like. I haven't done that yet, but I will look at currency pairs that are less liquid as well. Because you can think of, like, let's say that you do a price discovery paper and you usually just look at order flow, and in traditional markets we think that the linear price impacts are sort of fine, but here we actually know that we have a quadratic component, and at least for illiquid pairs or for large trades, I think it's important that we specify this in the estimations as well. Have you thought about like this square component in the price impacts before? I'm interested to hear what you think.
I not in this framing. I just thought about. So maybe one way to think about. Yeah. By the way, but everything here, right? All the analysis, right? We do it in terms of Uniswap version 2, kind of. because the way that I think about it is something in the constant product formula. I make it be that it's not going to be linear kind of by design. So once
Right.
we have so much usage of liquidity of one token, it will become it will push it to be like that. I don't know, like which can be a good feature in terms of, because it's, if we arrive to a situation that everyone want to buy one token, it's good that it's not going to be linear anymore. And it will, I don't know. Yeah, but I need to think about this new frame. And I actually like the presentation of the price impact. So I need to think about it.
Yeah.
What do you think about it?
I think that I'm sort of just taking a conservative stance in saying that I think it's important for estimation. So we correctly estimate price impacts when we sort of try to do this in a microstructure price discovery way or something like that. And then especially if we look at illiquid currency pairs. But I've talked to a lot of microstructure people doing research on these markets, and I think these are very hard questions that probably needs to do. Yeah, we probably need to do a lot more theoretical modeling and trying to understand sort of what the impacts are here. But anyways, this is I wanted to show you this this part at least, and yeah, and then I have some empirical results as well. I think I have a concluding slide regarding this part. Yeah, so trading can be deterministically mapped, and then we have this squared component that that I think is quite interesting. And then, of course, as we know, sort of the liquidity providers have a quite different role in this market. So they don't really revise quotes, and this is done by the constant product rule. So let's continue and look at some empirics here as well. So we know from this VECM that I talked about in the introduction that Binance drives the price for the USDC Ether currency pair. But then what is actually happening on Uniswap? So that's sort of the question that we can keep in mind for these few slides. So as I mentioned briefly, I have this Python package where I parse this data from Uniswap mostly. And one thing I do in this in this parsing is that I look at the to address in the Ethereum transaction, and I see which route this transaction has taken on the Ethereum network. So the first sort of category would be what I call direct trading. I think I call it manual trading in the paper. But this would be all the transactions that are sent directly to any Uniswap router protocol. And then I have these MEV smart contract arbitrage bots category, which would be any trade that is sent to a MEV bot. And then it can have internal transactions executing on Uniswap, but the to address in the transaction would be the MEV bot. And then everything else. So everything that is not a MEV smart contract or directly sent to Uniswap, I categorize as smart contract trading or DeFi trading. And this is just to sort of categorize every trade that is taking place or that is being executed. And yeah, we can look at some some just overview statistics here. So I don't know how. So liquidity provision really had a change in its volume here. Maybe maybe you know the reason for it. I don't really know, but and the MEV trading here, which I call arbitrage trading, was more prevalent, like 60% of the volume in the beginning, and then it has gone down a bit. But we can see that sort of the smart contract trading and the MEV trading are prevalent in terms of trading here. And then of course the concentrated liquidity design makes the liquidity provisions very high. So if you compare this to V2, for example, people are not as active as LPs here. The levels of liquidity provision volume is much lower. But
it doesn't necessarily so in figure 3,
yep.
Because it's in percentage, that means that LP could be doing exactly the same thing. It's just there's less trading going on. Or
Okay.
do we? Yeah.
Sure. Yeah, you're right. That could be the case. So I don't have any descriptive statistics here, but I know that I think the total amount of liquidity provisions for this sample period is over 200,000, if I remember correctly, and it's less than 100,000. Like I think it's like 60,000 or something for V2 for a longer. It's the same. It's the same.
And and then here when we think about LP volume, we're thinking about minting and burning.
Yes.
For V2, and then for V3, you also include adjusting positions.
Yes.
Okay, got it.
Exactly. So it's all sort of LP repositioning. So there are some papers. I don't know if you're familiar with the sort of Hasbrook VAR framework for price discovery, but there are papers in the microstructure literature that sort of decompose the order flow into different variables. So, for example, they look at algorithmic trading or high frequency trading and normal order flow, and they look at the influence of each of these groups to price discovery. And this is what I'm trying to do as well with these categorizations here. So I set up a VAR model where so I've done so many specifications of this model, and I get the same results for basically different types of lags. If I do it in transaction time or aggregate to 1 minute, and so forth. So it's quite robust. And what I do here is I look at the influence on return, on price impacts of these trade variables here. So we look at manual, the direct trading, algorithmic trading, and these MEV trades and liquidity provision, and we regress this in a system. I think I ran up to 100 lags on the on the trade time setup. So it's quite robust. And when we look at the impulse responses of this, we can see sort of these sort of classical Uniswap or MEV behaviors. So, for example, if we look at how the arbitrage or the MEV trades respond to a shock in manual trading, so we can see that this starts at 0 here. So we have a shock in manual trading, and sort of directly afterwards, you can see how the MEV trades trade in the opposite direction. And we will also see in in 2 slides from now or something like that, how the permanent price impact of these manual trades are actually completely reversed. So so this is a slide here. So this is the cumulative returns for the orders or the trades that are sent directly to Uniswap, and you can see that you have an initial price impact, which is defined by the immediate price impact equation that we looked at previously. So all the trades have this price impact depending on the liquidity and their order size. And then we have a MEV trading that reverse the price impact, and then it sort of over time reverses. And after about 10 trades, the price impact is completely reversed for the manual trading. And then we have these trades that go through 1inch and go through different DEX aggregators and so on. And they have a permanent price impact. They have some reversion afterwards, but they have some permanent price impact. And lastly, if we look at the MEV trades, I think this is quite interesting as well. So we have the price impact of a MEV trade. So we have one MEV trade, and then something is happening that is so this leg here is probably a sandwich, but this is an average representation of the sandwich trades that are happening. So you have a MEV trade that is increasing the price, and then something is increasing the price a bit, and then the MEV trades are trading in the opposite direction on trade 3. But in the end, leaving the long-term price impacted here. And the liquidity provisions, they don't have any price impact, which some people say it's it's by design or something like that. But to me, it's not clear that so they don't impact the mid price when they deposit or burn liquidity, but they could still in some way bring some kind of information to the market that other traders react to their behavior. But this sort of shows that they don't really have any impact. And what we can do with these impulse response functions is that we can calculate the percentage of their contribution by each trade group. And this is like very standard microstructure stuff. So this is from the Hasbrook papers, and he calls this information shares, and it's basically how much it's a variance decomposition in essence, where when you see how much these trade order flows contribute to the return. And this is what people also call price impact. So people say, for example, that these MEV trades, they have this amount of information share, and all the specifications, these MEV trades have around 90, 85, 90, 95%. I think the lowest is maybe 50% of different specifications. But this means that these arbitrageurs are basically driving price discovery in the Uniswap market. And to me, it sort of also concludes quite nicely with the VECM model, because we sort of think of that this market is a follower market where price discovery is happening on the centralized exchange, and then you have these MEV trades that are correcting the price accordingly. And this is also what we see in this table where these trades represent this large share.
Can
And we have this. Yeah,
question?
for sure. Just ask.
Yes. So I think that, as I see it, part of the 85% could be sandwich attack and manipulation attacks, which could look like a price discovery or information correction of the of the of the arbitrager. However, it's more like the arbitrager push price up or down of the regular trader and then fix it again. So do you have any way to say like how many activities are pure arbitrage that they are just correcting the price, and how many times it's just like they manipulate the price of the market and they just fix it?
Right. I think that would be depending on the time horizon of the impulse response and the regressions. So if you do like a very short transaction time analysis, maybe that could be the case.
Yes.
But
If you do it for a larger time horizon, it's less likely to be okay.
right, exactly. So then I would assume that the price would converge if it's weird, and then you would have centralized, decentralized arbitrage, for example, or something like that. So
I see.
I think they really have this they adjust these prices permanently.
And
Yeah.
then second question, in terms of control of your data, beside the stablecoin pair with Ethereum, did you also try two stablecoins or Bitcoin and Warp Ether to see if the pattern is same across different tokens, or each that there is not something else there?
Yeah, no, I'm going to write that comment down actually, because I think more. So I've done it for the top 10 largest currency pairs or something like that, but I have not done it for more illiquid pairs.
I see.
So yeah.
And something else that I have in mind is what's going on with tokens that only available to trade on Uniswap and are not in centralized exchanges. Um,
Right. I mean, I
so
think
there,
that's
I think the problem that you don't have a reference point. You don't know.
yeah. I mean, I think that's like super interesting, and I would really like to look into that, because so you have the mechanical arbitrages on chain, right? So let's say you have a currency pair that without any reference point, you don't have it's not trading on a centralized exchange. Then, like, my Mevbot could very easily check the the difference between SushiSwap and Uniswap and trade on that. But it wouldn't really, but that wouldn't really bring sort of any information to the market in terms of the value of this token. It wouldn't bring any private information or anything like that. So it would be only this like a mechanical correction. But in terms of evaluating this, yeah.
I see. So in some sense, you can mechanically capture if you have two liquidity pools, one in version T, one in version 2, or one in Uniswap, one in SushiSwap, whatever. You can mechanically capture which market is following the other by capture arbitrage activities, fixing price from one market to the other, but without saying nothing about the value of the asset. It's just to see like
Right. So in sort of regular markets and in crypto markets, we think of sort of like informed and uninformed and traders, and the informed traders bring information to the market and so forth. And I would assume something like that would of course happen in these less liquid pairs as well. But from the arbitrage and MEV part, yeah, that would be mechanic.
Okay.
Yeah, so some, yeah, I just had a slide with some conclusions here as well. Yeah, these arbitrageurs contribute to 50 to 90% of price discovery. And I can also say that, like, for example, 1inch, they actually contribute quite a lot as well. I mean, so in this currency pair, it's like 11%, and I think they have a really good way of detecting splitting their orders to sort of correct prices slightly and things like that. So they seem to, these smart contracts and DEX aggregators seem to do a good job there as well. But yeah, as we saw, these other trade groups, they have a relatively little impact on price discovery on these information shares, and it sort of aligns with the VECM estimation that we began with. So my co-authors and I, this is sort of the starting point here, and we are looking at some econometrics to do like estimate this in a good way and trying to think about this.